Let's look at an application of Stokes' theorem. In this particular case, we have a surface which is a plane and has the following triangular boundary. So this problem's given in a little bit different way, but the triangle has the following vertices: 3, 0, 0, 0, 3, 0, and 0, 0, 3. And so from that, we can actually get an equation of the plane and then project down into the XY plane to get the region R like we normally do when we do these types of integrals. But the computation is done like you would do in an Algebra 1 class. You take the intercepts x0, y0, and z0, and you form the equation for the plane: x divided by x0 plus y divided by y0 plus z divided by z0 equal 1. And then, of course, replace all the intercepts with the 3's and then cross multiply, and you get x plus y plus z equals 3. So that makes the problem very simple. And then, of course, when we project this equation into the XY plane, we just get a very simple triangle. So the problem looks difficult, but it actually isn't. So we can take this computation here and write the surface as z equal 3 minus x minus y. And then, of course, the region R is just described here by that projection, which I just mentioned. So again, this is pretty much like what we did in chapter 14 when we introduced the double integral. And so what we want to do in this particular problem, like we did in the last, is compute the line integral of f about this triangle. So we can see again why Stokes' theorem might be a little bit easier here. We don't have to parameterize the boundary of the triangle, and so maybe we would opt for the double integral as an easier alternative. So first, we want to think about computing a normal. So we look at this construction, negative zx, negative zy1, using this particular equation. So we get a negative 1 and a negative 1 with additive inverses give us 1, 1, and then of course the other one which comes along by construction. So we get a very simple computation here. And then of course we need the curl of f, so we do the nabla cross the vector field f. So we do a 2, 3, so in this case we get a 0, and then the 3, 2, we have the z, so we get the minus 3, and then we do 3, 1, so we have the partial here, which is 0, and then 1, 3, we get a partial of 1, so we have 0 minus 1, and then lastly 1, 2, we get a 0, and then 2, 1, we get a 2, so we have a 0 minus a 2 to give us a curl vector of negative 3, negative 1, negative 2. Again, we wish all the problems were this easy. And now, when we actually apply Stokes' theorem, we replace the line integral with the surface integral of the curl. So again, we put in the computation for curl, negative 3, comma, negative 1, comma, negative 2, and dot that with our computation for the normal, which is this vector here, 1, comma, 1, comma, 1, integrated with respect to x and y, or just dA. Your choice as to what you like to use. dx, dy is fine. We're not necessarily implying an order of integration, but dA is fine, dx, dy, whichever you choose. And here, notice, when we do this dot product, we just get a negative 3 plus a negative 1 plus a negative 2, which is a negative 6. So just like the last video, when we factor the negative 6, we actually have the area for the region R, which is very simple. This is just the area of that right triangle. So that's 1/2 base times height, the base being 3 and the height being 3. So we get the negative 6, 1/2 base times height, and of course the 2 absorbs the 2 in the negative 6. That leaves us 3 copies of 3 with a negative, so we get a negative 27. So what's good about this particular computation is that it highlights the idea of being able to compute a plane using the intercepts. We have done this before, but it has been a while, and we are done.